All right, so let's talk about the first of the major circuit elements that we're going to deal with, and that's capacitors. So again, just to remind ourselves, what is a capacitor? Well, it's a device for storing energy in an electric field. Basically, with any type of capacitor, what you're doing is you're taking two plates, separating them by some short distance, charging those plates, one with a positive amount of charge, one with a negative amount of charge. Again, there'll be a potential difference across those plates. And so this is the equation that really is going to define what's going on across your capacitor. So notice what it tells you is the amount of charge that you can store on your plates is going to be equal to the capacitance times the potential difference across your plates. Now, what we're going to tend to do is, again, we're just going to say, well, the potential difference, we know that that's really a difference from one plate to the other, but we're just going to write it as the voltage across our capacitor, and so not worry about the delta, even though, again, we know that it really has to be there. So this equation is basically going to be our Ohm's law for capacitors. Ohm's law is the, V equals IR is the equation that will what we'll call Ohm's law, that's an equation for resistors, and that defines what's going on with a resistor. This is basically the same kind of idea for a capacitor. It's the equation that defines what's going on with a capacitor. Now we can rewrite this equation, and so if we solve this, what it says is that the capacitance is just this ratio of charge to voltage. And so what that's really meaning is that what the capacitance is trying to tell you is how much charge you can store at a given voltage. So if you have something that has a very large capacitance, then you can store a much larger amount of charge at a given particular voltage. So that's sort of fundamentally what the capacitance is trying to let you know. All right, so here's a very simple circuit. Now, one thing to sort of point out is notice that this Q is basically, generally we define this to be positive and we define this to be positive, right? You'll notice that the total charge you store on your capacitor is actually always zero because you're putting a positive amount of charge on one plate and a negative amount of charge on the other. So when we're talking about the charge stored, really what we mean is the charge stored on the positive plate. Right? Because the charge stored on the total capacitor is really always zero. But what the capacitance is telling you is that, just thinking about this very simple circuit here, well, our loop rule says that whatever I gain across the battery, I'm going to have to drop across the capacitor. So the voltage of my battery's got to be equal to the voltage of my capacitor. So whatever the voltage of the battery is, that's going to determine the voltage across my capacitor. And then how much charge I can actually store on those plates, that's going to be dictated by the capacitance. And again, the larger you make the capacitance, the more charge you can store on those plates at a particular voltage. Again, in units, the units of capacitance are, well, charge per volts, which is known as farads. And usually, almost always, we talk about capacitors that have very small farads, microfarads, nanofarads, picofarads. All right, so again, fundamentally, kind of how does this work? Well, basically what you do is you start, when you hook your capacitor up to a battery and close the switch, effectively what happens is you're going to start moving charges around. And so for a parallel plate capacitor, which is what this is, notice that what we've got is two plates that are parallel to each other. They're the same shape. The capacitance of your parallel plate capacitor is really just defined by the geometry. So what's the area of your plates, and then what's the distance of separation between them. So what dictates the capacitance is really a function of geometry. And so then when you start moving charges around, right, so hey, maybe what I'm doing is I'm, literally taking electrons off of this plate, running them around, all the way around my circuit, adding electrons over here, right? So what I end up with is a negatively charged plate on this side, a positively charged plate on that side, and as I put more and more charges, right, increase the charge on each of my plates, I basically build up the electric field. So that at the end, I have a fully charged capacitor that has as strong an electric field as it's going to have, and I've stored as much energy as I possibly can. So that's sort of, that's the picture of what's going on when you charge a capacitor. All right, so how much energy is stored in a capacitor? Well, sort of fundamentally what we're doing is we're basically moving some tiny little charge from one plate to another. And so we know that the energy stored, well, that's just the increase in the potential energy. That's got to be equal to the work that you do, which is just going to be, well, add up all the work you did to move every single one of those charges. Now, when you move the first one, when the plates weren't charged, that didn't require any work. But as you get more and more charge on each of the plates, and it looks like we're going to build positive charge over here and negative charge over there, so as you get more and more positive charges over here, it becomes harder and harder to move the next one across in terms of just thinking about the work required. So the work here is just going to be, well, our little charge times the change in potential, right? That's going to be, that's how we're changing the potential energy. So Q delta V, we basically are just writing it as V, the voltage, times dQ. And so dQ, well, we know that we can write that as C, because that's just the capacitance that's dictated by the geometry of my capacitor, times, as I move these charges, I basically change the voltage a little bit, because as I build up more and more charges over here, I'm going to increase the potential difference between my two plates. So when I go to plug this in, I'm going to end up doing this integral so that at the end I can think of this as being, well, zero charge or zero voltage at my negative plate, and whatever the maximum voltage I have across the plates at my positive plate. And so when I go and do the integral, then that tells me what my limits are. So from 0 to V of C comes V dV. So all we did is took our dQ is C dV and plugged that in and just pulled the C out front. And so you notice that C, that again, that's just a constant, just depends on the geometry. I can pull that outside of my integral, and I'm left with the integral of V dV, right? So the voltage times the differential voltage element, and so I know that's going to be 1/2 V squared. And again, when I evaluate that at the endpoints, it gives me this. So the energy stored within my capacitor, one way to think about it is it's just 1/2 times the capacitance times the voltage across your plates squared. Okay? Well, because I know, right, I have my Ohm's law for capacitors, right, I know that Q equals CV. Well, CV, and then there's a second V left over, so I can rewrite this as 1/2 QV. That's also got to be a way to calculate the energy stored within my capacitor. And then again, well, let's see, V is just Q over C, so I can get rid of the V by multiplying this Q times the second Q over C, and that gives me a third way of calculating this as 1/2 Q squared over C. So all of these are just equivalent ways to calculate the energy stored within the capacitor. And what we'll see is thinking about the energy stored within a capacitor is going to give us a way to check and make sure through conservation of energy that we've got the correct answers when we've got a series of capacitors hooked up to a battery. And so that's why this is going to end up being important in terms of to make sure that we're not violating conservation of energy with our circuit.